Okay, so today I want to tell you how the Fourier transform helps solve equations. So, I will study several examples, and actually the examples we already studied. The wave equation is, in a sense, the most complicated one. The problem we are solving is the following. We have some inhomogeneous equation like this. With some function in the right hand side. One option is this, another option is the heat equation. Or maybe it can be the multi-dimensional heat equation. It also makes sense. Or it can be a Poisson equation. Laplacian of u of x in many dimensions equals to f of x. So, of course, we can write a few more examples, but let us concentrate on these ones. So, the idea which worked in the finite dimensional case was that if we apply a Fourier transform to this equation, then it drastically simplifies in the Fourier modes. Let us do this with some of these equations, and let us start with the simplest one, with the heat equation. Maybe we can do this even in a multidimensional case from the very beginning. On R1 plus, or on R times R n. This corresponds to t, this corresponds to x. So we have an equation like this, and we want to substitute all the functions as Fourier transforms of something. So let us say that u of t and x is the integral d omega over 2 pi d p over 2 pi to power n. And here there is a different convention for the Fourier transform for time and for coordinates. So for time it looks like minus I omega t. For coordinates is I px. Where? To pi to power n, or what is what is the question? So we can substitute as a Fourier transform, and we can do the same with the right hand side. So the same integral f tilde of omega and p. And so then, when we act with time and coordinate derivatives, the only part of this formula where they can act is this. We have explicit time dependence in the exponential, and we have explicit x dependence in the exponential. So what happens if we act on such an expression with dt minus Laplacian?
Why does I omega t have minus and
Uh,
I
It's a kind of convention. One motivation might come from special relativity, because if you think that omega and p are components of some vector, and t and x are also components of a vector, then their scalar product should be computed using Minkowski metric. But in this case, there is no Minkowski space, so we can take it just as a convention. So, but it doesn't matter. You can choose a different convention. It cannot affect the answer in any way. It just adds some minus sign somewhere. Yeah, so Laplace operator is of course a sum of d2 over dx I squared. So what happens if we act with this operator on the exponential?
minus I omega plus p squared?
Yes, because no, y minus, there is I which becomes squared, so plus. So,
Why'd you put the plus sign? You're using a plus convention?
but you differentiate it twice. So let us.
Oh, sorry, it's minus the Laplacian. Yeah, you're right.
So in the simplest example, minus dx squared or dxx acting on e to minus I omega t plus IPX is so change this formula. That is minus I omega plus p squared e to minus I omega t plus px. So if you look at the Fourier components, such operators act just by a multiplication by some function. So dt goes to minus I omega, dxi goes to I p I. Well, maybe let's choose some different number. So, or if you write it in the vector notation, then gradient goes to I p. And the Fourier transform. Uh, Again, now if you substitute into the equation, then what do we get? We get that 0 equals to the integral d omega over 2 pi dn p over 2 pi to n minus I omega plus p squared u tilde minus f tilde. So this is 0. So if the Fourier transform of some function is 0, then this function is also 0. So we can solve this equation, writing that u tilde is f tilde over minus I omega plus p squared. Right? So we can write it in a slightly different way, in a more universal way. That u tilde, the Fourier transform, equals to some function g tilde times f tilde. And in this particular case, g tilde will be 1 over minus I omega plus p squared. It is called the Fourier image of the gain function. And you see that it is super easy to obtain. We simply take the differential operator on the left hand side and perform this replacement everywhere. So, are there any questions about this?
So we take u tilde and f tilde function, and then the Fourier transform, and we say that, and we are assuming that you solve this equation with some function f, and then
Yes.
we have that u tilde and f tilde have to have some form this time.
In a sense, they're expressed in terms of gain function. Yeah. So, so, so in some sense, we have already solved this equation. If we think about the Fourier transforms. But of course, we would like to have these formulas in the coordinate representation. And let us go there. So the question is, what happens in the coordinate space? Well, we actually studied this question, maybe in a slightly different situation on S1, but the question is general. What happens with coordinate representations of functions when we multiply their Fourier images? So, uh, namely, let us say that there are u and u tilde, and u tilde, g and g tilde, which is again a Fourier transform of this. G is a Fourier transform of g tilde, which we still need to compute. And there is f and f tilde. Those are Fourier transforms. We have that relation, and that u tilde is g tilde times f tilde. And this should correspond to a relation between these functions in coordinate space. So let me write this relation like this. So we have already seen this character at some point. Let me write it again. It's called convolution. So the question is, what is the convolution? Let us just compute this explicitly. So we know that we know that there is this formula for two Fourier transforms, and we want to take the inverse Fourier transform of this product. Let me write for simplicity all these vectors for the Fourier transform in kind of four vector notations, simply omitting that they have different components for time and for coordinate. So let us write that there are formulas like this. Tilde is sorry, g tilde is the integral of e to minus ipx g of x dx dn plus, oh, let me also, let me write this numbers of integrations. G tilde of p f tilde of t, I have the same expression. So this is what happens on the right-hand side, and in the left-hand side, we want to switch back from the Fourier image to the original function in the coordinate space. So we need to write the A inverse Fourier transform. that u of x is integral so we have these three formulas, and we simply need to combine all of them together. So u of x is therefore this integral dn plus 1 p over pi to n plus 1 e to I px. And then let's substitute this to other integrals. Over some other coordinate to avoid the collision of notation. So I've simply substituted on these two integrals that define corresponding Fourier transforms. So, are there any questions so far? So then let us proceed further. Mm. So we have a triple integral. Like, yeah, like this. So, and who knows? Can we compute at least one of those integrals? Mm, yes, because there is a single place where p enters this formula. And we can compute on this integral. A delta function with what coefficient?
Well, we have to use the factor 2 pi over n plus 1.
Yes, it will be cancelled.
Yeah.
So we can write it as integral dn plus 1 x prime dn plus 1 x 2 primes delta of x minus x prime minus x 2 primes g of x prime of x 2 primes. And now we can also compute one of these two integrals. For example, the integral in x prime, because there is a delta function. that puts x prime equal to x minus x two primes. So it will equal simply to integral over x in two primes g of x minus x two primes f of x two primes. Which I denoted by convolution. So this is what we call convolution. So are there any questions? Yes, so this was the first explanation of this formula. And I can also show the second explanation of the same statement. Uh, So we want to solve some equation with some differential operator in the left hand side. So we have some differential operator that depends on gradient acts on function u of x and gives f of x. So in order to solve this, we can represent its right-hand side as a combination of delta functions. So we can write it tautologically in the following way, that it is the integral over dn plus 1 x x 2 primes, for example, delta of x minus x 2 primes. Let me draw this x in red. So we expand the right-hand side as a linear combination of functions of x, and these functions are delta functions with coefficients equal to f of x primes. This is more or less what we did in the finite dimensional case. And now, if we learn how to solve this equation for the delta function of right-hand side, then we will be able to solve it for the arbitrary right-hand side. So now we first need to solve it for delta function on the right-hand side. So when this differential operator acts on f of x, and it gives a delta function. So it's g of x. So g is a given function. So it's a solution of our equation with a delta function on right hand side. Then we can notice that if this is solved, then we can substitute the gain function of a difference. And what will we get in the right hand side, do you think? Everything lives on Rn. So what happens if we shift the argument of a gain function by some constant?
Well, the measure stays the same if you're just shifting by a constant.
Yes. So this function had singularity at 0, producing this delta function. So this function has exactly the same singularity at x primes, and this will also produce a delta function, but at a different point. So is it clear or not?
It's the delta function at x minus x prime.
Mm-hmm. Yes. So this was a delta function concentrated at 0, and this is a delta function shifted to a point x 2 primes. Right? So
The delta is still on x or is in x minus x?
uh,
No, sorry, number.
yes, I should have written this. All these numbers are in x.
Okay.
X 2 primes is just a parameter.
Okay.
Yes. So now we have this building block. We have a solution for a point like source on the right hand side. And now let us do this. Let us combine it with our function f of x 2 primes. So d of gradient of x acting on the integral d of x minus x 2 primes f of x 2 primes dx 2 primes. This is what we had into this equation equals to integral of delta x minus x primes f of x primes dx 2 primes. Oh, and this equals to f of x. So we see that the right hand side equals to our differential operator acting on this convolution between gain function and the right hand side. So it is indeed the solution of our equation. So, but this was written under the assumption that we know the gain function. Um, but we still need to compute it somehow. And if you try to solve this equation, it can be done in several different ways, and it's actually an advantage of such an approach, because the simpler equation is, the more methods to solve it we have. But one of the obvious approaches is the same. Like, we can do the same procedure, but for the delta function on the right hand side, mm, and simply write it in Fourier components.
So for different equations, these different methods, some will be easier than others.
Yes, in a sense, this equation is mostly free, so we need to find a solution of the with zero right hand side, and then add something at one point. In a sense, some boundary conditions at one point.
What do you mean when you say that the equation is free?
Hmm?
What do you mean when you say that the equation is free?
I mean that it has nothing on the right hand side except at one point. So maybe. So if you take for image of this, then uh, we will get a Fourier transform of G, which is G tilde, and as we checked here, all derivatives should be replaced by IP. So this differential operator acting on the Fourier transform turns into D of IP. D of IP times G hat. And what is the Fourier transform of delta function?
Step function?
No.
What, the delta function?
Well, let's just take the definition of the Fourier transform. Delta of x tilde is the integral over dx e to minus ipx delta of x. So, what?
We completed this integral like two lectures ago,
Mm-hmm.
and I think it's like minus I e to the
E to what? Mm. Mm. But what? Mm. So, yes, yes. Yes. Because it's simply the integral of a delta function that lends us to 0. And the value of this exponential is 0. Mm. So if we want to compute the inverse transform, then we need to introduce some regularization. Like, if we want to make sure that Fourier transform of one is a delta function, we need to do something, because the delta function can only appear as a limit of some delta X sequence. But in this direction, it's pretty simple. So if we know this, then we know that the right side, hand side of this equation is 1, and therefore for a transform of the gain function is 1 over this differential operator with derivatives replaced by IP. And you see that it is something quite generic. It can naively be applied to any equation, and it also extends to difference equations. Because if we shift x by some vector, then this exponential is multiplied by the exponential of I shift times x. So mm, mm, we can do the same for difference equations. And as a result, we will simply get some exponentials of p in this. So this can be called a symbol of this differential operator. Particular case of it. So, are there any questions about this?
When we write one over the operator, we are
Hmm?
it's the inverse of the operator.
But it's an operator acting on the Fourier modes, and we check that when it acts on Fourier modes, then all derivatives are replaced with IP, or if there is a dedicated time direction, then it is minus I omega. So it was simply some polynomial like here. So let me write these equations mm, side by side by side. So 1 over minus omega squared plus p squared. What else? For example, this. Sorry. Uh, Maybe let me. Well, that's fine. Px squared plus py squared. Something like the same with non-trivial mass. Or maybe m squared minus dxx. And so on. By the way, we can see why I told that in the wave equation we already studied is the most complicated case. It is because this Fourier image of the Lagrange function has singularities when omega equals to p or to minus p. So there is an entire cone, and it is the same in all higher dimensions. So it will require a special treatment. But other operators are better. So
The fractional Gaussian as
uh,
a Fourier transform. So do these techniques work with fractional
yes,
operators?
yes, of course. Mm. And I would say even more that if we want to define fractional derivatives, then one of the most natural ways is to define them first in the Fourier space as simple operators of multiplication by fractional power of p, and then find how to write it in coordinate space. So there will be some differential, there will be some integral operators. Okay, so are there any other questions? Okay, so far we have developed some kind of general formalism that up to some details can be applied to any equation. But there is still the last fifth step on this way, or maybe one of the intermediate steps on this way, and this it is a step on which we need to actually compute the green function coordinate space. Uh, so let us do it in our case of uh, the heat equation. So g of t and x is d omega over pi d np over pi to n. So I propose to compute this integral variable by variable. So, namely, what happens if you try to integrate it in omega? Do you know how to compute such integrals or how to approach them?
We have both. So one of the recipe theorem and complexify.
Yes. So there is variable omega, and if I draw the analytic structure of this integral in the complex plane, we find a pole at IP squared, and that's all. So the omega plane. So then, if time is negative, then we can close this. Mm, let me think. Mm, Oh, if time is positive, we can close this integral in the lower half plane, Oh, wait, let me think. If I made any mistake, yes, of course, I made a mistake because it is not IP squared, it's minus IP squared. Sorry. Okay. Now, if time is negative, then we can then this expression decays in the positive imaginary direction, and we can close this contour in this way. So this is for time less than 0. When time is positive, we can close this contour in the lower half plane. So we know that there is a theta function, a Heaviside theta of t, and uh, mm, when t is positive, we still need to compute this integral. We need to compute the residue. Mm. And what is this residue? What do you think? So we can write on this here that 1 over minus I omega plus mm, p squared is I over I times omega plus I p squared, and this integral is computed in the clockwise direction. So we'll have extra minus sign because of the direction and factor of 2 pi I. So I will simply write the answer that this integral altogether so it gives 2 pi I that comes from the residue computation. Then there is minus 1 that comes from direction because it's clockwise, not anti-clockwise. Times I, between this I, and then we need to substitute the remaining expression where omega is a substitute with minus I p squared times there was also 1 over 2 pi and that were in the original integral. So it is a value of omega, its residue, plus IPX. All right. Do you have any questions about this?
Which classes of equations can't be solved with Fourier transform?
Can't be or can be.
Cannot be.
Uh, if all homogeneous, no, how to call it, all equations that don't have explicit coordinate dependence can be solved by Fourier transform. And if they have a coordinate dependence, but over some directions, then we can perform Fourier transform over the rest of the directions. So it's one possibility. Another possibility is when the equation does not have translational symmetry in any of the directions, but has some other symmetry. In this case, we should use some different transform, which is friendly to that symmetry. We will see such examples mm, in spherical or angular symmetrical problems. In that case, there is a kind of different version of such discrete transform where we use spherical harmonics instead of exponentials. So the Fourier transform was just a transition to some convenient basis in the space of functions, and these functions were convenient because they were eigenfunctions of translation operators. But there are other examples. For example, we can take eigenfunctions of some of the rotational operators. So they are called spherical harmonics. And, hmm? Okay. Okay, let's continue our computation. So we have a lot of numbers here, and most of them can be cancelled. Like all these numbers cancel. Also, these two i's cancel as well. So we have a heaviside theta of t, saying that the Lagrange function vanishes for negative t's, times the integral d n p over pi to n e2 minus t times p squared. P is a vector plus ipx. So, and to compute this integral, we need to know something about so-called Gaussian integrals. Let me write it, for example, here. So these integrals form a basis of a modern quantum field theory, because it's more or less the only integral which people can compute in the multidimensional case. So, mm, so let's study them. Well, the simplest example is of course this. Do you know the value of this integral? Mm-hmm. Yes, and do you know how to prove this?
You square the integral and then
Mm-hmm.
put a spherical coordinates.
Yes. So, and does everyone know this? Not. Yeah. Okay. Just in case in this computation, minus r squared times I squared is minus r squared to pi rho d into rho from 0 to infinity, which is precisely pi. Yeah. So it was the simplest in case. Then we can perform an upgrade. Mm. And here we need to ask a little bit for convergence of this integral. Namely, we would like to have a real part of A greater or equal than 0. Because if it is negative, then this integral is divergent. So what happens if we do this? Yes, thanks. Now the next upgrade. We add here the linear term under the same conditions. So now we can gather the full square in the exponential. Plus b squared over 4a, like this. And now we can say that this is a new integration variable. We simply shift it. And this can be done also for complex B and A. This shift will go in the, in principle, it can go in the imaginary direction. But since the integration domain for this integral is from minus infinity to plus infinity, and the integrand decays in this direction, then these shifts do not matter. In a sense, if we write that x minus b over 2a is x prime, and this x prime is complex, in a sense, this integration contour shifts in the x-plane shifts to some other integration contour in the complex plane, like this one. Then it does not matter, because we can move this contour to the real line at infinities. We can draw it like this. because the integral in this domains behaves like e2 minus ax squared, so it goes to 0. Contributions from this parts of integration domain go to 0. And so we can draw a contour like this. And the last step, we move this contour back to the real line. So even if this shift by b over 2a was complex, the integral will be the same. It doesn't have singularities anywhere in the complex plane, so we can move this contour freely. Yeah, but we don't even need to think about this. We can simply write this integral equals to a integral from minus infinity to plus infinity e to minus a x prime squared plus b squared over 4a dx prime, which is a square root of p over a e to b squared over 4a. Well, this is this is almost what we need there. Let us consider even a more general situation when maybe let me number this integrals. Let us consider even a more general situation when x is a vector. So in this case, we can write it as a product of independent integrals. So we can write it as a product of e to minus a xi squared plus bi xi dnx. And write as a square root of p over a, well, p over a to power n over 2 times, how would you write this part using vector notation? Yes, well, a norm is like a scalar product, or it's just b squared over 4a, right? And there is also the most general formula, which describes the case where we have an arbitrary quadratic form in this integral. But we will not need this. But the formula is this: if you have x ax plus a scalar product, then it equals to pi to n over 2 divided by square root of determinant. And times times the exponential of 1/4 b a inverse b. So this b squared over a is actually an avatar of a inverse quadratic form. So this part can actually be proved quite easily. You simply need to adjust the shift of x in this n-dimensional space so that linear term disappears. And this determinant can be obtained by diagonalization of quadratic form. So you can first diagonalize it and then compute each of the integrals. And this requires trivial transformations in the n-dimensional space. And for our purposes, this formula would be sufficient. Okay, so taking this formula and applying it to our integral, let's finish the computation. So first, we had originally to pi n in the denominator, and this combines with this expression. So we'll have 1 over 4 pi t to power n over 2. This one, that part. And we also have the second part times e to minus x squared over 4t. So the answer x vector squared. So I can probably erase the beginning of this computation. So we simply take this gain function and write a convolution of it. Of course, I forgot the initial prefactor besides it of t. So we have an integral in t prime from minus infinity to t because we have a heaviside theta in the gain function. we have integral over the whole space, dn x prime. We have this gain function of a difference n over 2. So mm, see this squared. This is this pretty simple integral. Mm, sorry, one more mistake. Oh, like this. Which is pretty simple integral, which is well defined actually for any possible function on the right hand side. If it doesn't go to infinity faster than e to x squared. But usually people study this for bounded continuous functions. And what else? By the way, we obtain this gain function by computing this Fourier transform, but you can also try to check that it actually satisfies this equation. So the right hand side might be problematic, but you can check that this equation is satisfied everywhere except t equals to t prime. So it's a simple exercise. You can do this. I'll probably add it to the list of exercises. Yeah. So. Yes. Thank you. Thank you. Yes. Thanks. Oh, by the way, it's a good question. What happens if we choose f to be time independent? And it leads us to the idea of a reduction from more complicated to simple green functions. So let me do this. Yes, so originally we had this equation. U of t and x was f of t and x. So let us do something with this equation with a typo, which will not be a typo this time. So let's say that f of t and x is just f of x. There is no time dependence. Then it is a natural assumption to think that u is also time independent. Is also u of x. But if it is time independent, what is the equation solved by this u? So it is this Poisson equation. Yeah. Minus Laplacian of u of x equals to f of x. So if this limit exists, then we can get one more green function just for free. So let us check this. So to be sure that everything works, we need to check that if we substitute such kind of initial condition, which is time independent, into this formula with a green function, then we get a time independent solution. So let's simply do this. So u of, in principle, it could be some u of t and x, but let us see how it works. We have integral in dx prime. We have the integral from minus infinity to let me say to 0, because since there is no t prime dependence, we can shift t by t prime and say that t minus prime is a new integration variable. dt 1 over 4 pi t so it's dt prime. Oh, let me call t minus t prime by some variable lambda or tau. Then the integral in tau will be from 0 to infinity. The tau 1 over 5 or 4 pi tau to d over 2 to so so we need to compute this integral and say that it is a new green function, reduced green function, or green function of Laplace operator. So first let us check that this integral makes sense. It is definitely convergent for t small to for t equals to 0, because if x is different from x prime, and this exponential goes to 0 much faster than 1 over tau to any power goes to infinity. And it is also convergent for big taus, because this exponential goes to 1, and if d is greater than 2, then this integral is also convergent. So we simply need to compute this. But this integral is slightly inconvenient because we have 1 over tau in the exponential, we have all these prefactors, and to compute this, let me introduce a new variable, lambda, which is all this expression in the exponential. And let me further introduce a notation for x minus x prime. Let me call this r. So let me write it as r squared over 4 tau. Then so first write the integration measure. So let me also write a formula for tau. Tau is 4r. It is r squared over 4 lambda. So d tau is minus r squared over 4 lambda squared. There is also this prefactor 1 over 4 pi tau to d over 2, and it equals to lambda to d over 2. And 1 over 4 pi to d over 2 times 2 over r to our d. So let us combine everything together and write that the gain function is the integral from 0 to infinity d lambda lambda to d minus 2 over 2, maybe d over 2 minus 1, e2 minus lambda times r over 2 squared times 2 over r to power d 1 over 4 pi to power d over 2. right? Sorry, it's d over 2 minus 2 actually. Yes, because we had lambda squared. So, do you know the value of such integral?
Looks like one of the special functions.
Yes, and the special function is called gamma function. Yes, so let me write it in this corner. So integral from 0 to infinity d lambda to p minus 1 e minus lambda equals by definition to gamma of p. And this gamma of p satisfies the same current relation as factorial. Gamma of p plus 1 equals p gamma of p. And it can be checked using integration by parts. So we can identify gamma of p plus 1 with p factorial. There is also a less trivial equation satisfied by this gamma function, namely it is this. And one of the corollaries of this relation is that a gamma of 1/2 is a square root of pi. But this square root of pi is the same square root of pi as in the Gaussian integral, and it can be checked by explicit computation of this integral after the change of coordinates. So in principle, this cancellation and this extra value are sufficient to compute this integral for any possible value of d, for odd and for even. Yes, so using this definition of the gamma function, we can write that it is gamma of d over 2 minus 1 1 over 4 pi 2 d over 2 times 2 over r 2 d minus 2. So we can simply write that it is some constant that depends on d. So I probably have changed n to d at some point, maybe here. Let me restore original notation for dimension of the space. So it is some coefficient C of n divided by r to d minus 2. It's r to n minus 2. So, indeed, our assumption worked, and the solution of this equation is given by the reduced gain function. So we have computed this gain function, and so a reduced solution u of t and x is indeed u of x, and is given by the integral over dnx prime c of n, absolute value of x minus x prime to n minus 2 f of x prime. So this is a gain function of the Poisson equation. We also see that and the gain function for the heat equation was the best of those, because it was not problematic at all. This integral was variable convergent, which is not obvious in this case. And also there is another problem, that if we decide to compute this gain function for n equals to 2, this naive answer does not work, and we need to think a little bit more. Maybe let me do this in the remaining a few minutes. By the way, do you have any questions about this, or is it fine? By the way, since there is also next lecture, let me simply tell you the answer for n equals to 2. That in that case, gain function will be proportional to logarithm. And we will discuss this later in more detail when we actually come to these equations. And also another remark that what I was telling before was more or less in the first part of the Bruin's lectures, but this time I jumped ahead and told something that was written at the beginning of section 4. In the case of the heat equation, probably something like section 2 or 3 in the case of Poisson equation, because I simply wanted to show what we can already solve using the Fourier transform. And so those were problems that are simple and can be solved immediately, but there are of course many other questions which we'll study individually for all these equations, because it's the only thing that can be done universally. We can compute green functions and um, mm, uh, express them in terms of Fourier transforms. But even the computation of these green functions in cases of particular equations are different, and you see it even here for the heat equation, for the Poisson equation. And there are also other differences, so this has to be studied individually for our equations. So, do you have any questions? Okay, then thanks for your attention, and see you next week.